I have a few different type of strong neodymium magnets and some viewing film so we can see what's going on. So here we see it can go on the center. That must not be where the ring of energy is. That's not where the ring of energy is. That's not where the ring of energy is. Ah. Doesn't want to go there. I can feel the bulge around there. So those so-called magnetic lines of force is actually a ring of energy. Even when a square object spins around, it will trace a circle. Every object, no matter what shape it is, will trace a circle. And there's the ring. The ring will appear as a line because we're looking at it from the wrong angle. Just as this appears as a line, but is it really a line? No. It's a circle, a ring. And is a circle really a circle? No. It's either a ring or a sphere. There are no magnetic lines of force because we are in a 3D world and there can't just exist a line. A line is always a part of something else, part of a 3D object. So what looks like a line is actually something else from another angle. Very pronounced here. So we go by the notion that this half is positive and this half is negative. But what I'm seeing here is a negative and a negative with a ring of positive. But yet, when you put one of these together, it wants to stay. When you put the negative to the negative, it wants to repel. Or is that what's really happening? Walter Russell says Coulomb's law is flawed. And I trust Walter Russell. It's not a line. Feels more like an accretion disk, not a line. Let's go back to this bar magnet really quickly. This line that they say of force, I say is actually a ring. And it would be as if this object is spinning like that, constantly with a ring of energy around it.
Everyone knows it's Slinky. Everyone knows it's Slinky.
Everyone loves a slinky. And I like to go by what I call the slinky law. Anything you can do with a slinky, you do with a magnet, and vice versa. So, you see the magnet wants to attract this paper clip in all sorts of ways. But it doesn't want to attract it here. So, this means that anything you can do with a magnet, you can do with a slinky. If this can go on the top, this can go on the top. If this can go on the side, the paper clip can go on the side. Go on the bottom, and this can go on the bottom. This can't go on the rim because there's that bulge of positive energy there. Positive energy is repulsive. It's repelling the metal. Just like this is repelling it and blocking it from going in here. So this can go that way. I can go this way. Now let's look at what two magnets together look like. Let's want to stick together like that. These two can stick together like that. And twist this to the side, and it doesn't want to go in. I twist this to the side, and that holds true. Okay. Now, this can go around, and it will always go around in perfect proportion. Let's mark this. And as this travels around, it'll always travel in perfect proportion. Okay, so it's like this is on a gear almost, and it won't ever get off of that gear. Just like when these are locked together, this can move around, but it's locked on the gears of the slinky. Now I'll get into another thing later, what John Searle calls plate charge, and he says that when his machines are running in a person's car or in an aircraft or an inverse gravity vehicle, they can't crash and they can't knock together. And this is because of plate charge. You increase the charge, meaning you increase the density of that magnetic field. Now, even though they could come together before, this is so dense now that it won't stick together. So, if this is somebody on the freeway, this will be very dense all the way around their ring. Now, if this is somebody at the stop sign and they pull out in front of somebody, you literally won't be able to have an accident because you are in your car and then the magnetic field is around your vehicle. And so as you're traveling, this will always keep you safe. Coulomb's law is flawed. Opposites do not attract. Like attracts like. This is like to this, therefore it will be attracted, and it will stay. This is not like, so it's not going to be able to go in there. This is like to this, so it can go on the top into the gear. But it can also go on the bottom. And here's where we encounter the confusion, because either way, this can go on this gear. But this is not stationary. Neither is this. With these magnets, we do not have a stationary field. The field itself is going in on the top and out on the bottom. But it's still negative, and this is still negative, and this is positive. But yet, this negative field is going in. We're watching the flow of the flux. We're not watching the polarity. We're watching the way that the magnetic current flows. So it flows in like this, just like we see in the diagrams. In, out the bottom. In, out the bottom. But the path that this actually takes, I drew a phi spiral on here, very faint, you can barely see that. Path goes in, and if you were to draw it out flat, you get the infinity sign, because it will constantly loop in and out of that toroid. So this is constantly moving this way. This is constantly moving this way. So if this is blowing out on the bottom, and this is blowing out on the bottom, is this going to be able to touch this end when they're both blowing out on the bottom? No. Does that have to do with polarity? Not a bit. It has to do with the flow of current. You're going against the grain here, so therefore it will be repulsive. And you're going with the grain here, so therefore it's going to connect on top. And on the side, it'll connect.
Everyone knows it's Linky. Everyone knows it's Linky.